I want to go over what we learned hopefully last year in our study of projectile motion. So I think the first and most important thing to say about the concept of projectile motion is, once again, this is a parametric motion, right? That we have a motion in the x dimension and the y dimension that are happening simultaneously yet independently of each other. That notion of the independence of dimension is absolutely critical, right? The only thing that is linking our motions here is the parameter of time, right? Because we know the x position changes as a function of time, and so does the y position. Now, this particular parametric motion that we know of when we're talking about projectile motion, remember that the x acceleration here is going to be 0, meaning that there are no forces that are acting horizontally on this object once it has been launched. So we are talking about it post the launching process. And in the y direction, the acceleration being experienced is negative g j hat, right? Or I could say g down if I want to take my declaration and make down positive. But that is the formal way of saying it. So there's a constant vertical acceleration, but a 0 x acceleration. And that's the main thing of the projectile motion bit. And then we're just going to go from there. So what does this mean? That means that horizontally this object moves at a constant velocity, while vertically the velocity is constantly changing, right? And it's changing in a downwards direction. So if I fire it up, it's going to slow down on the way up, hit an apex, and then speed up on the way down, just in the same way that our throwing up problems functioned during chapter 2. So I think the best way to do this is by looking at a problem. That way I can illustrate how our chapter 2 problem solving methodologies are no different than what's happening here. So let's tackle what would have been a hard problem from last year. So let's say I have a cannon being fired off of a cliff. Let's say I know that the cliff here is, I don't know, 150 meters tall. And let's say that the initial velocity of this launch, let's say we know that that has a magnitude of, I don't know, 200 meters per second. Let's say that that initial angle of launch is, we'll just go a basic 30 degrees, right? So that's this. And so I'm just going to draw in the trajectory of this object. And our goal is to find when it lands here. And I want to know when does it land, where does it land, as well as what is its speed when it lands. There are some other things that we could want to note that we'll talk about. So how do we do this problem? Well, the same way we did our our chapter 2 problems. We are going to start with a picture, got my picture. Boom, there it is. Next, we're going to do axes and declarations. So here's the thing. It is super important in these problems that we define an origin. Where is x equal to 0? Where is y equal to 0? Now there's a couple of logical places that we could put it. We can make our start equal to 0. I'm actually going to make this point equal to the 0, 0, 0, and I'm going to say up is positive and to the right is positive, okay? So what are we going to do from there after we've got this? Well, then we're going to start on our knowns, because actually we should ask ourselves, do we need to partition this problem? No, because I'm not being asked about trip up or trip down. I'm just being asked about total trip because of the way I framed the problem. So here we go. And so the way we're going to partition this problem, though, is not based on space or based on time. We're going to partition by dimension. And I'm going to write down my knowns separately for x and for y. So xi, xf, vix, vfx, ax, yi, yf, viy, vfy, ay. Okay? Now, we're going to put here a line, and then we're going to do our times. So time total is the time that I care about. I'm going to put that down here. If I cared about a time up or whatever, I put that down there. Because the times are not attached to any of the dimensions. They are the parameter that links our two dimensions. So let's see what we know here. Well, based on this, we know that xi is equal to 0. I'm looking for xf. Vix. Well, I don't have Vix, and so that's the other thing that we know about these projectile motion problems, is that I need to find the components of my initial velocity in order to do this. So Vix and Viy, I'm going to do that little side work. And we do have to show some work here, folks. You can't just randomly assert stuff, right? And so that's going to be 200 meters per second cosine of 30. I think I know what that is off the top of my head, but I'd rather be right and slower, right? 173.2 meters per second. And then Viy is equal to Vi sine of theta I, and that's going to be 200 meters per second sine of 30 degrees, and that is of course just 100. And we're just finding the magnitudes here. We'll assign them directionality when we put them down here onto our chart. So Vix then apparently is a positive 173.2 meters per second. We know from the context of the problem that there is no x acceleration, right? Because it's in free fall throughout the entire course of the motion. There's no forces acting horizontally on it. That means I already know that Vfx has to be exactly equal to Vix. Awesome. Now here, this is where choosing your origin actually has some import, because Vi now, or Yi now, is that positive 150 meters. If I had chosen here, my Yi would be 0, and then my Yf would have been negative 150 meters, because I'd be 150 meters below that. Right? Notice still we're going with positions. We're not going displacements, because these problems get harder. We don't actually want to know displacements. We want to know positions because we want to know when things intersect. That'll make a lot more sense as we get into this. So Yf here is 0, right? The final height that we're getting to that I care about is at the base of the cliff. Viy is positive 100 meters per second. It's fired upwards. Vfy, I don't know, I want that. And Ay, because I said up is positive, therefore it's negative 9.8 meters per second. Okay, so that's what I've got. And so now, generally with these problems, we're always going to approach them in the exact same way. Now, first off, you'll note I wrote my table in the center, because what I'm going to do is X work here, Y work there, because I want to have a nice organization. With projectile motion problems, it is the very rare projectile motion problem that the first thing that you shouldn't do is write down the equation of motion independently for each dimension. So here we go. Yi plus Viy t plus 1/2 Ay t squared. Generally, this is what's going to happen. Now, this term zeroes out, and you may be asking yourself, why even write it? Because this is a more advanced course, guys, that we're going to have problems where Ax isn't equal to 0, right? That's going to be one of the weird variations that we're going to talk about here, which is why we're simultaneously talking about just generic parametric motion, right? In fact, one of the problems that we did today in class had an Ax that wasn't equal to 0, was equal to 2/3 meters per second, but I digress. So let's just plug in what we know here. I know I want that, but I don't have the time. Great, but that doesn't mean I'm just gonna leave that space there, because when I find the time, I already have the work done for it, right? So let's come back over here and we'll do this one. So I know that this is 0 meters, and look, first plug in, folks, I've got all my units. The units are gonna go away after my first plug-in though, as they start to get a little bit annoying. Now, notice here I'm going TT because I care about the total time. We're not doing some sort of segmented partition of this problem. If I was doing time up or time down, I would want to have a slightly different notation there. Boom. And so when I look at this, I'm like, okay, well, that's just standard quadratic equation. I'm just going to put it into normal form there, just to make it a little bit easier. Negative 4.9 t total squared, and then this is plus 100 t total plus 150. You have calculators. I'm just going to do the quadratic equation real quick. I guess I could have just fired up Desmos and put it in there. Would have probably been a lot quicker, but I'm already invested. And once you're already invested, you should just sort of like plow through. There we go. Over 2 times negative 4.9. Okay, cool. So what I'm going to do here is I'm going to find out what the square root of the discriminant is, what all of that good stuff is, because that's going to be helpful for me. okay? And then when I calculate that, I find that that is 113 point, we'll just go 0.8 there, all over negative 9.8. Now, it's a quadratic equation, which means it has two roots, so there's two answers to this. So I'm gonna generate both of them, even though one of them might be negative, because sometimes one of them is not negative. We wanna get in the habit of finding all the mathematical solutions to our problems when they are offered to us. So let's do the other root. Okay, and this one does indeed come out negative, a negative 1.41 seconds. So 3 digits there in each one. So therefore I now know my T total. Boom, there it is. I've got it. And so that's one of my objectives. I can come back over here now and just plop that right in. That's 173.2 meters per second, and then T total is 21.8 seconds. Okay. All right, and that gives us a very large range. And by the way, that is an important piece of vocabulary. The final x displacement is called the range, right? That's called the range, like a driving range or a golfing range. And apparently a range here is like 3.76 or 78 kilometers, which is kind of ridiculous. But then again, I said it's a cannon launching off a cliff. All right, now the last thing I said is I wanted the speed. Well, the speed here, I would have to know both the x and y components of that final velocity, because the speed is going to be the magnitude of that final vector, that VF vector. So I've already got VFX, so let's find VFY. I'm going to do that right here, so find VFY. Okay, our objective here, I guess our objective here was to find the time. Okay. So find VFY, so here we go. VFY is going to be VIY plus AYT total. So that's going to be 100 meters per second plus negative 9.8 meters per second, and then 21.8 seconds. Throw that into your calculator, and you will find out that that answer is negative 113.8 meters per second, right? Or within rounding. You'll note that that is the same number as this number here. And there's good reasons for that, because this equation is just a rewriting of the VF squared is equal to VI squared plus 2A delta Y, right? So it does come out the same. So now that I've got my VFY, I can find out, I'm going to do this right in the center, that my final speed then, or VF, is going to be the sum of the square root of the squares of VFX squared plus VFY squared, which is the square root of, what were those numbers? 173.2 meters per second quantity squared plus negative 113.8 meters per second quantity squared. Throw that into our calculator. 113.8 squared plus 173.2 squared, square root of quantity, and you get that this answer is 207.2 meters per second, which should make sense. It should make sense that it is faster than the initial speed because it had time to go up and then come back down. So what are some other things that we could want in this problem? Well, I could want, what is this maximum height, right? And if I wanted that, I would have to partition the problem and just look at, say, the trip up. Now, who would care about the trip up x? What I would do then, if I wanted this, I would make this a YT column, and then it would make a Y up column. And then that would be the initial position on the Y up, the final position on the Y up, the initial Y velocity on the way up, the final Y velocity on the way up, and AY during that, right? Because who cares about like this X position? I could also maybe want to know the speed at that point. There's all sorts of other things that I could want to know as a partition. But generally, with these projectile motion problems, we're going to partition always by dimension, and then sometimes partition the Y motion by up, down, or other parts depending on what's going on. So that's really the basics when it comes to projectile motion from everything that you saw last year. What we're going to do is play around with this a little bit more, talking a little bit more about min and max problems with this, as well as talk about what are going to be called interrupted path problems. And that's what we're going to be spending the balance of our class time on, talking about generic parametric motion and these more advanced versions of these problems.